Hello, Professor Wu. This is my submission for the extra credit video tutorial. Today I'll be explaining a non-Newtonian fluid with an example. So shown here is a graph that is relating shear rate to shear stress. The black solid straight line that goes through the origin and is linear is for Newtonian fluids because their relationship to strain rate and viscosity is linear, and therefore viscosity coefficients can be determined easily or more easily. The other two curves, the blue one and the orange one, are non-linear, as you can see. So the shear thickening curve, the blue one on the top, as the strain rate is increasing, the viscosity is increasing. For the shear thinning curve, the orange one, as strain rate increases, the viscosity decreases. Today I'll be doing an example of a shear thickening fluid, also known as a dilatant fluid. So to show you that, first I have another paper slide to show an equation here. This is a power law equation where this n term is the viscosity, the k term is a material constant, and this epsilon dot is the strain rate, and here is n, which is the power. So for a non-Newtonian fluid, a shear thickening fluid to be precise, requires that this n be equal to at least 2. Now for the example. What I prepared today is a batch of what's called oobleck. And this is a suspension of cornstarch particles in water. And because of the particle size and the shape and their distribution in the water and the relative amounts, this is a shear thickening fluid. So it's interesting because at high strain rates, it acts as a solid, and at low strain rates, it acts as a liquid. So right now it's slowly dripping off the spoon, but if I were to tap it, it acts like a solid. It's very interesting. So as I'm very quickly increasing the shear rate, the viscosity is increasing very quickly at that moment also, so much so that it appears to be solid. Because a fluid is described or defined as a substance that is continuously deformed when shear stress is applied, such as water deforms very easily, oobleck will not do this because it is non-Newtonian where water is Newtonian. It's almost upside down right now. So for the next example, I will do a punch test, as I like to call it. I can get this spoon out of here. easily. Get the oobleck off. Okay, so right now I'm about to perform the infamous punch test. So most fluids, when you punch them, they will splash everywhere. But since I am trained in the art of fluid mechanics, I trust that my desk and my shirt will not be affected by punching this fluid, because I know that punching it applies a very great shear rate, so the viscosity will increase and it will act as I'm punching a solid and not a liquid. So stand by. Punch. Nothing, virtually nothing on my fist. But if I go very slowly, say with a finger, and just slowly penetrate it, I can even stir my finger around if I move slowly enough. So at slow strain rates, it acts very fluid-like. Whereas this was acting as a solid only a moment ago, I can assure you it feels very fluid right now. And then I can even pick this up. And at slow strain rates, the fluid was moving all over my hand, and see here, it got stuck. So there you have it, folks. That is an example of a non-Newtonian fluid, and that is science being cool and fun. So thank you, Chin, for a great semester. I learned a lot, and I hope you enjoyed this video. I hope the quality was okay, and I hope that you also have a great summer. This is Adam Albers, signing off. Thanks, Chin.